If you've ever taken a math class, you've probably met SOHCAHTOA, right? It's kind of the rock star of solving triangles. But what if I told you that for centuries, this trusted method had a huge, massive blind spot? Well, let's uncover the tools you need to solve any triangle.
Here's the deal. SOHCAHTOA is amazing. It's incredibly powerful, but it has one rule it absolutely cannot break. It only works if you have a right angle. It's designed just for right-angled triangles. That's its entire universe.
So, that makes you wonder, what about all the other triangles out there? The ones that are slanted or stretched out or kind of squashed? The ones without that perfect 90-degree corner? It's time to figure out how we solve those.
To handle any triangle that gets thrown your way, we have to move beyond the basics. It's time to upgrade our mathematical toolbox. And today, we're going to add two incredibly powerful tools that will let you crack any triangle problem you ever see.
Okay, but wait. Before we crack open this toolbox, we need to get on the same page about one really simple but totally critical thing. And that's how we name the parts of a triangle. Trust me, this little convention is the key that unlocks the power of everything else.
And it's actually super simple. Look here. Angle A, that's the big capital letter, is always directly across from side A, the little lowercase letter. Same goes for angle B, opposite side B, and angle C, opposite side C. Keeping this straight makes the rules we're about to learn way cleaner and a whole lot easier to remember.
All right, toolbox is open. Let's pull out our first tool. This is the sine rule. I want you to think of this as your flexible, all-purpose measuring tool. It's perfect for a ton of different situations.
The funny thing is, the core idea behind the sine rule is probably something you already know intuitively, like from 5th grade. It just makes sense, right? The biggest angle in a triangle is always staring across at the longest side. And the teeniest, tiniest angle, well, it's facing the shortest side. The sine rule just takes that gut feeling and turns it into a precise mathematical formula.
And boom, here it is. What this elegant little formula is saying is that the ratio of a side's length to the sine of its opposite angle is the exact same for all three pairs in the triangle. It perfectly captures that relationship we were just talking about, directly linking the length of a side to the size of its opposite angle.
So how do we actually use this thing? Let's walk through an example. Let's say we know two angles and one side. So angle A is 30 degrees, angle B is 45, and side A is 10. We just set up the proportion from our rule just like you see in step 2. 10 over the sine of 30 equals B over the sine of 45. You do a little bit of algebra and bam, we find that side B has to be 10 times the square root of 2. See, it's that direct.
But here's the thing, like any really powerful tool, the sine rule comes with a user manual. And maybe, more importantly, a big flashing warning label. There is a hidden trap here, and you absolutely need to know what it is.
Okay, seriously, pay close attention to this next part. This is the one little detail that trips up everybody, even really experienced students. It's called the ambiguous case, and it can lead to some seriously tricky problems if you're not ready for it.
So the central question is this. Under what specific circumstances can you plug all your numbers into the sine rule and discover that there isn't just one right answer, but two completely different triangles that could fit your data?
Well, this little problem pops up when you know two sides and an angle that is not sandwiched between them. We call this the side-side angle, or SSA case. As you can see in the diagram, that third side can kind of swing back and forth, creating two totally valid triangles, one with a sharp, acute angle and another with a wide, obtuse angle. And both of them satisfy the exact same starting information. Crazy, right?
And hey, don't just take my word for it that this is a big deal. The source material for this explainer specifically points out that high-level math competitions, we're talking the Olympiads, they love to use this trap. It's how they test if you have a really deep understanding. So the takeaway is simple. If you see a side-side angle problem, slow down, proceed with caution.
So, that leads to an obvious question. How do we deal with that sine rule trap? Well, let's go back to our toolbox and grab our second tool. This is the cosine rule. And if the sine rule was our versatile measuring tape, the cosine rule, well, this is our heavy-duty power tool. It's for the tough jobs where the sine rule just won't cut it. Honestly, the best way to get your head around the cosine rule is to think of it as a souped-up version of a formula you definitely already know. I love this description of it. It's basically the Pythagorean theorem, a squared plus b squared equals c squared, but with an extra piece bolted on to correct for the slant. And here is the formula itself. Just look at it. See how it starts? C squared equals a squared plus b squared. That's pure Pythagoras. But then you see that bit at the end, the minus 2ab times the cosine of angle C? That is the correction factor. That's the magic piece that adjusts the formula so it works for any angle, not just a perfect 90 degrees.
Let's see this thing in action. Imagine you know two sides and the angle that's squished right between them. So, sides 5 and 7, with a 60-degree angle tucked in there. You literally just plug those numbers straight into the formula. C squared equals 5 squared plus 7 squared minus 2 times 5 times 7 times the cosine of 60. You crunch the numbers and you get your answer. C is the square root of 39. That's it. No ambiguity, no second possibility. Just one solid, clean answer.
So now we have two awesome tools in our toolbox, the sine rule and the cosine rule. Which brings us to the most practical, most important part of all, the user manual. How do you decide which one to pull out for the job?
This is the question, right? When you're staring down a triangle problem with a bunch of sides and angles, which rule do you grab?
Okay, this table right here, this is your ultimate cheat sheet. If you know two angles in any side, you're going to use the sine rule. If you know two sides and the angle between them, or if you happen to know all three sides, that's a job for the cosine rule. And if you get that tricky case with two sides and a non-included angle, our old friend SSA, you're back to the sine rule, but remember that warning label. You've got to use it carefully. Phew, we have covered a ton of ground. We've gone from the limits of good old SOHK TOA to a full-blown toolbox that can solve any triangle on the planet. So now, it's time for you to get your hands dirty with your first project.
Okay, you have the tools. Now it is your turn. Here is your challenge. Two sides of a triangle are 10 and 12. The angle opposite the side with length 10 is 30 degrees. So how many different triangles can you build with that information? 1, 2, none? I'll let you think about it. The answer? Well, it might just surprise you.
Have you ever looked at a Ferris wheel and thought about a radio wave? I know, it sounds kind of weird, like a riddle, right? But believe it or not, we're about to connect those two things and find some really elegant math that's been hiding right under our noses. So let's just jump right in. Seriously, how does a Ferris wheel relate to a sound wave? It feels like a total stretch. I mean, a giant metal ride at a carnival, explaining something invisible like sound or light. But the connection? It's actually super simple. It really just boils down to one single thing, a repeating pattern.
Okay, so here's the big idea, the aha moment. Just picture yourself on a Ferris wheel. Your height, right? It's always changing, but in this really smooth, totally predictable way. You go up, then you go down, and then you go up again, over and over. That's simple motion. That's it. That is the visual blueprint for sine and cosine waves.
All right, so we've got the basic concept down. Now let's get into the cool part. How do we actually take that spinning circular motion and turn it into a wave you can draw on a graph? We're going to build it together, piece by piece.
Okay, first things first. Picture you're sitting in one of the cars, just a single point on the edge of that big spinning wheel. As you start moving, all we're going to do is keep an eye on your height, just your vertical height. You start at the middle, right? Height 0. Then, as the wheel turns up, your height gets bigger and bigger. And now for the magic trick. I love this part. Imagine we can just grab that circular path you're traveling and unroll it. Just straighten it out into a flat line. That line, that's our x-axis. It's basically tracking how far around the circle you've gone in degrees. And then, for every point along that line, we plot how high you were. That's our y-axis. And boom, there it is. Look at what happens. At 0 degrees, you're at height 0. You get to the very top, that's 90 degrees, you're at your peak height. Then at 180 degrees, you're back down to the middle again. Keep going, 270 degrees, you're at the very bottom. And finally, at 360, you're right back where you started, one full trip. What you're looking at, that's a sine wave. So we've just met the sine wave, but you know, it's not an only child. It's got family. Meet its sibling, cosine, and their, let's call it quirky cousin, tangent. They all come from that exact same spinning circle, but they each have their own personality. Okay, this is super important. Sine and cosine. They're basically twins. It's the same exact wave. The only difference is where they start. Think about it. Sine starts at height 0, right? That's like us watching the Ferris wheel from the moment you get on at the boarding platform. Cosine, on the other hand, starts at the very top, at its peak height. It's the same up and down ride. We just started the stopwatch at a different time.
All right, let's talk about tangent. This one's the rule breaker, the rebel of the family. Its whole identity is built on a really simple formula. You just take the sine value and divide it by the cosine value. Now, you might remember from math class, what happens when you try to divide by 0? Yeah, things get a little dramatic.
So because tangent is sine times divided by cosine, anytime that cosine value hits 0, the whole thing just breaks. It goes haywire. This is what creates those vertical lines we call asymptotes. They're like walls that the graph gets infinitely close to but can never ever touch. It just shoots off to infinity. So yeah, tangent is a totally different kind of beast. It's got this unique, much faster pattern.
Okay, so we've met the whole family. Now comes the really powerful part. Let's learn how to take these basic waves and tweak them, control them. Think of it like we have a control panel with 3 main dials. By turning these dials, we can go from a generic wave to something super specific, like the sound wave of a guitar string or a radio signal. We can literally create any wave we want.
So our first dial is called amplitude, and all this is the height of the wave. How tall does it get? We measure it from the middle line up to the very highest point, or the peak. Going back to our Ferris wheel, this is like changing how big the wheel is. A bigger wheel means a bigger radius, which means you go way higher and way lower. That's amplitude.
The rule for this is super simple. If you see a formula like y equals a sine of x, the amplitude is just the absolute value of that number a out in front. So, let's try one. If our equation is y equals 3 sine of x, what do you think the amplitude is?
Yep, it's 3. Exactly. The wave is now 3 times taller. It stretches all the way up to a peak of 3 and down to a bottom of -3. The basic shape is the same, it's just stretched. See? It's really that easy.
All right, dial number 2, the period. This one is all about speed, or you could think of it as frequency. It's just the length of one full cycle. How long does it take before the pattern starts repeating itself? A shorter period means a faster, more compressed wave. Just like a Ferris wheel that's spinning really fast completes a full circle in less time. Now the number that controls the period is this b value. It's the number that's multiplying the x inside the function. And the rule is, the period is just 360 degrees divided by b. So, if we have the equation y equals sine of 2x, what's our new period going to be?
You got it. 360 divided by 2 is 180 degrees. So the wave gets squished horizontally. It has to complete its entire up and down journey in just 180 degrees instead of 360. It's literally vibrating twice as fast. Okay, last dial. This one's called the phase shift. And this is probably the easiest concept of the 3. It's just sliding the whole wave left or right. That's it. You're not changing its height, you're not changing its speed, you're just changing its starting point.
Now here's the one little catch, and honestly this trips a lot of people up, so listen close. When you see a plus c inside the parentheses, it actually moves the graph to the left, and when you see a minus c, it moves it to the right. I know, it's a total opposite of what feels natural. So with that in mind, what's going to happen with y equals sine of x minus 30 degrees?
That's it. The whole wave just slides 30 degrees to the right. You just have to burn that weird rule into your brain. Minus means right, plus means left. Just lock it in and you'll be good to go.
Okay, we've got our 3 controls down. Amplitude for height, period for speed, and phase shift for position. Now it's time to put it all together. Let's look at the kind of problem you might actually see on a test and just solve it.
Okay, let's look at this one. Y equals 4 sine of 3x. We don't have to guess, we just apply our rules. Step 1, look for the a value. That's the number out front. It's 4, so the amplitude is 4. Simple. Step 2, look for the b value. That's the number next to the x. It's 3. So the period is 360 divided by 3, which is 120 degrees. And just like that, you know the 2 most important things about this wave. See how that works? Hey, you want to know the most common mistakes people make? Let me give you the cheat sheet so you can avoid them. First, amplitude is a height, so it's always positive, even if there's a negative sign out front. Second, remember the period formula is 360 divided by b, not multiplied. Third, don't forget that weird phase shift rule. Plus is left, minus is right. And last, remember that a bigger b value makes the wave tighter and faster, not wider. Keep those in mind and you'll sidestep all the common traps. So think about this. We started with the simple Ferris wheel, and now we have a formula that can literally describe any wave. That's the real takeaway here. You now have the toolkit to describe so many repeating patterns in our world. We're talking about everything from the sound of a guitar to the rhythm of the ocean tides, even the electricity flowing through the walls of your house. They're all just waves. So the question is, Now that you can build any wave you want, what patterns in your world could you describe?